Yeah, thanks a lot for kind introduction. I think the irony is that indeed we never really worked on the lines between research and industry, and I'm feeling funny in the industry track. So we were from the start very much research focused, and Lion is a non-profit research organization, which is though very punk self-organized thing. And this is also a tale here of the communities that were rising because of a particular issue in machine learning field as a science field, that the core of machine learning research, the foundation models, were developed behind closed doors, and that created also a strange situation in academia that you couldn't study them and reproduce them properly and so on. I think to make the story proper, I have to tell first what are the foundation models, because this is quite an ill-posed, I think, still terminology. I think chronologically the story goes is that before 2000, I don't know, 13 is a strange number, let's say 10, machine learning went the way that you had your experiments done, training models for very narrow domains, solving very specific tasks, and they were working there halfway, but then you couldn't transfer them across various conditions. So learning was poorly transferable, and you had to train long and then landing up with models that are not reusable in the end. So it was also inefficient, but also scientifically unsolved how to transfer properly. So, and then there was some core breakthroughs since 2012 or so, which was showing that you actually can train generic models that then are transferred well across various conditions. So you could then take some bunch of data that is then a generic one, and not belonging to any particular narrow domain, and then have a model that is then, after so-called pre-training, adaptable in efficient manner to other downstream tasks where you have small amounts of data only available. So learning the transfers across tasks became possible, and the hints for that were quite early there. So for instance, for the vision community with convolutional networks, people saw that you can have this off-the-shelf features when you take pre-trained networks back then, things like overfit, and then of course ResNets in 2015. So you could see also that those generically pre-trained backbones are also beating everything that you can train from scratch on the small amounts of data in specific domains if you do the transfer. So that was basically the breakthrough, that all of a sudden problems that had small amounts of data were solvable. And then we had this development that is, I think, known to most of us, that the models and data became larger and larger at scale for a particular reason. So it was not that just for fun people had available compute. That was actually not the case. But the scaling up had a very clear reason in empirical observations, and then backed up also by theory, which changed actually the paradigm that was there in classical machine learning before, that large models are actually bad and would overfit. So people saw that actually increasing model data and compute scale during pre-training hand-in-hand results in this steady improvement of the function, especially when it comes to transfer of the models resulting from the increased scale procedures. And especially the performance was boosted in those cases where you had the a small data regime of transfer, so zero shots, zero shot, few shot learning was boosted very strongly. And this is an old figure from the GPT paper from 2020, GPT-3 paper from 2020, where you see that the smaller models slightly above 1 billion parameter, do not really show this interesting functionality. Here's this in context learning case of grasping the task immediately from just the prompts, whereas the, well, 2 orders of magnitude larger models are able to do so. And here's, not shown really that also the data scale of pre-training is larger. So then that was leading to this so-called scaling laws observations, where people then measured systematically what happens if you vary scale during pre-training, and they saw that things like upstream test loss is going down steadily, and also downstream error on various tasks are getting smaller and smaller. So you get it granted that your model capabilities are improving just by increasing scale. You don't really innovate algorithmically in such cases, right? So, and then this gives us somewhat the properties, a set of properties that are there for a model to be a foundation. So you have this generic pre-training that is meant to be scalable. So you have generic data. Usually it's still text image or text image. You have quite simple losses that are driving learning. And you have important is self-supervised training. So this gives you the way to have data scalable, because then you can gather it from, say, public internet via a common crawl, and you are not relying on this heavy labor of human labeling anymore. So the generic pre-training, one thing, then data efficient transferability is the property that you obtain after such a pre-training. And especially zero-shot, few-shot, and small data transfer becomes strongly performant. So, and the one thing that is sometimes forgotten, that's why I was accentuating it so much, so scaling laws have to be derived for such a model. So if you just observe something that works well across different tasks after pre-training, it's not the end of the story. You have to show that you get this performance boost granted if you just decrease scales across various dimensions, so model size, data, and a sample seen during the training. And if you derive this loss for your model class, then you can call it foundation. So we have a number of foundation models. Language, GPT, BERT, T5, vision, well, arguably ResNets because it's still supervised training, not really scalable on the data side. But Dino, for instance, is dealing with self-supervised training mode, and there you can scale your data nicely. So, but language vision is most prominently here, a clip from OpenAI, and then stable diffusion. That came from a diffusion model class. There you can just collect image text from public internet, and then you have the data scalability given much better than for, let's say, pure vision. So long-term story of all of it is, of course, that people in machine learning were always aiming for this one model for all. So you would like to have universal architecture that then results in generalist learning that is strongly transferable across various conditions once you have it done. To be able to study, to obtain and study such models, you then need to have these things covered here. So to have large generic data sets, to be able to handle models of larger scales, and to be able also to afford long training in the pre-training phase. If you're able to do this, then you obtain building blocks that are meanwhile fundaments for the whole field in different domains. So language vision, arguably audio. So the problem was and still is, of course, that research of this kind can be executed only in few large industry labs because they have the resources, and meanwhile also by self-amplification, the people who have expertise to drive such experiments at all. So this leads to a major problem for science, first of all, because these artifacts are non-reproducible. You can, of course, trust the paper, but you cannot really check it at all. So this is maybe the first thing that we were worried about. And all others are resulting from that. So you can also argue that, so there is this debate about safety. You can, of course, argue that safety is also kind of limited, also given in the hands of very few people. So who decide then, what are the safe procedures? Maybe they all have good intentions, but also do mistakes by checking up the safety, so nobody can check what's going on. So this closed data and models were worrying the community for a while, and then there was a rise of grassroots research communities that aimed then to open source and study those important artifacts that are foundations for the field. In USA, there was a Loiter AI upcoming, so big science, who trained Bloom, the first large language model on European grounds, was rising in France and hijacking their supercomputer Jean-Zay in Paris-Saclay. And Lion then appeared in Germany. So was formed as a non-profit research organization then around early spring 2021. And then we also copy-pasted the big science effort, and our big machine was Jülich-based machine standing in Jülich Supercomputing Center, Jewels Booster. So we needed to tackle these three pillars in order to actually at all execute the experiments to obtain the models I was now talking about. We decided to go for language vision, which resulted to our ties to model class CLIP, contrastive language image pre-training, and open CLIP community that open sourced the first version of the code base for the community to try on. So there were certain things missing. Large-scale data was not there, so most of the data sets were behind the closed doors. I mean, not most, all. So there was basically no data set to work with. We then had to take care about obtaining this large-scale compute and also gather somehow people who have enough expertise to drive such experiments. So we then did some steps to get this covered. On the data side, there was really a grassroots community effort that has nothing to do with supercomputing. There were really like people in the best punk hacker tradition sitting around, distributed across the globe on their home PCs, on some cloud resources, crawling via command crawl that creates mirrors of internet since a while, public internet for the data set that could have then scale sufficient enough for such experiments, which resulted then in these two data sets, line 400M and line 5B. And line 5B got then high acclaim from the scientific community by getting outstanding paper award at NeurIPS 2022 for a good reason, because it was not only, I think, a collection of the data set, but also its validation. So we took OpenClip code, involved OpenClip community in replicating the OpenAI results, and also provided actually a full scaling law version for this model class that is fully reproducible then, and everybody can check up on it, and also reuse the models that we have trained in open source manner. So and these data sets and models were then disseminating the whole community a lot. For instance, maybe the most well-known industry dissemination of this kind was then the appearance of stable diffusion. That was also a research project on German grounds in Heidelberg and Munich. That just used the Lion collected data and OpenClip pre-trained models to build their stuff then and go for the industry track. So for compute, we were applying for publicly funded supercomputers. So all foremost Jewels Booster at Jülich Supercomputing Center, where we were anyway sitting and already doing large-scale experiments, so it was easy for us to continue the same. Then we went also to USA, to Oak Ridge, and applied for Summit. That is an older machine, but still good enough to play around with. And there are also a lot of opportunities for orange PC calls that we would also then take to get additional resources. So you have to imagine the scale of such machines as having a couple of thousand GPUs at least, because for the experiments you would have to execute, you really need at least hundreds per experiment. So this is an example of Jewels Booster instantiated in Jülich Supercomputing Center November 2020. Already an older machine. Even older one that we got in USA is Summit, having almost 30,000 of old V100 GPUs. But there you can also gather the expertise in distributed training by just trying what happens if you go to many thousands of GPUs. So this is not straightforward, and everybody has to do this exercise in order to deal with such experiments. So going from tens of GPUs to hundreds is a step, from hundreds to thousands is equally a difficult step. So So, and this served actually as magnets. So these machines are indeed becoming hubs to attract people with expertise in core machine learning, but with less expertise in actually doing large-scale distributed computing, and then become in few weeks or months experts in doing so. So this is a really a clear fertilization story here. Different strong labs without access to proper compute are just getting attached to organizations like Lion, and there is a win-win situation. So basically people bring in their expertise from core machine learning, and organizations like Lion provide them with workflows how to do it on the larger scale. This community that is grassroots in the sense that it's not only strong research labs, but a lot of citizen scientists, coders, and so on. This is the real strength of Lion, in addition to the available compute resources. And you can very quickly instantiate projects of different kind by just pinging people who already know the workflows around larger machines and so on. This, of course, can fertilize industry also very well. If people decide to go for industry track, they have all the expertise they need actually to do it also on larger scale by getting in touch with communities like Lion. So as a short overview so far, what happened that we studied and open sourced some important model classes, like again OpenClip, that is representation learning, a strong backbone for very different kind of language vision tasks. Stable diffusion was strongly pushed by both dataset collection and model training from our side. So OpenClip is a critical component in stable diffusion. Without it, it wouldn't work this way at all. Then we also have a look now on interleaved multimodal language vision learning like Flamingo. So OpenFlamingo was released as well by Lion, and then language models, so of different kind, also here for the community to try. So foundation data sets, this is not a terminology yet, but I would call it, so data sets that are reused across very different research scenarios to study the actual properties of learning. Line 400M, Line 5B, the most prominent ones, but there are also now follow-up works like DataComp, that is community-based challenge to actually exercise how to do proper subset selection data set that improves model performance systematically if you do the proper filtering of a raw large pool data. So DataComp is like the next step after the Lion collection that was quite chaotic and had to be done out of despair. So now with enough resources available, we can do it way more systematically with initiatives like DataComp. So to give an idea about timeline of such a development that went from closed source to open source, one example is here, which deals with different language vision models. At the beginning, so one have to say that OpenAI is scientifically a very fruitful endeavor, right? So that they have chosen a closed source model is one thing, but they are the strongest scientific, among the strongest scientific players in the field, and they always give the community the right directions to go. So this they did with two systems, Clip and DALI, that were completely closed-doored. Nobody had an idea, is it true? Is it just generated by some trick? And then shortly afterwards, the data sets of the sufficient scale from Lion came up with funny-wise different closed doors models like Imagen or Party, reusing them for their own purposes. But then it came then at some point open source release of OpenClip that enabled stable diffusion. And then from then on, open source community have actually strong cards to also push a bit, to make some pressure on the closed doors schemes to actually participate in this common development, because they just getting afraid to fall back. So they kind of forced to give some insights back to open source, not to get isolated in this movement. So we got some here national and international feedback after doing so, and this visibility was, of course, good to attract more people and more resources to do this kind of open source research. And to be able to do so, I would like to give an example what actually happened in a case of OpenClip, which is a foundation model for language vision, an important one because currently, arguably, the strongest backbone for all kind of vision-based tasks is obtained by taking a vision encoder from a pre-trained clip or OpenClip models that have then a very strong transfer functionality, especially in zero-shot and few-shot case. So first thing you have to do is to collect data to feed such a thing. That was line 400M5B. That is then a workflow for itself with different stages that is completely open sourced and everybody can replicate it and try it on their own, or an improvement, of course. So once you take care about the data set collection and the data set is in place, you can also improve these procedures, which is then undertaken by the DataComp initiative. So Lion is not a static, Lion datasets are not a static thing, so there will be follow-up versions that actually have a clearly measurable effect then on the model quality that you obtain by training on it. What you can do then with a large-scale data set like this is you can vary the scale systematically to obtain the scaling laws that was so important for claiming the foundation model status. So this is just one example for OpenClip VIT architecture on 3 discrete model scales and 3 discrete data set scales and 3 discrete samples in scales. So you execute these experiments, which are very costly for even middle scales. You obtain, in this case, is only one particular task shown, zero-shot ImageNet, 1K top 1 accuracy. We have usually a standardized benchmarks that cover a range of tasks, so we don't assess it only for one particular, even important task. They do it on a broader range, and then we can see the trends on scaling laws across tasks and are sure, yes, this is not some singular phenomenon. It actually shows improvement with scale across different settings. So again, for this one particular task, you obtain such points that you can then put on a plot that visualizes on x-axis the total compute invested per each experiment, and then the downstream performance on zero-shot ImageNet. And then you get this, linear trend that is power law form, because here we have a log plot type. So in this power law shows you the predictability of the performance with a variation of compute scale. And then you are sure that you have a model that is actually growing in performance just by investing in compute during the pre-training. So this you do across different tasks. This is shown now for one task. In blue is the OpenAI work that has, unfortunately, only 3 points. So fitting a line through 3 points is, of course, a bad modeling exercise. But so you can also then compare the models against each other and see whether there are interesting trends, either depending on the data set that you have used or on the training procedure and so on. So you can, of course, use it to predict performance on larger unseen scales, and this is the whole point. Then you are able to decide what you do next on the larger scales. So you do these experiments on small and mid scales, and afterwards you get your proper systematic measures and can fit a law. You use it to plan your moonshot. So those are then ingredients for a reproducible open foundation model that one have together to drive this kind of open science, open source based research. You have to take care about both data set composition to be open and all the pre-training routines to be open, together with benchmarks that are open and reproducible, so that the community can do the model comparison and decide what to do next. So the stable diffusion is one example of such a story, how different open source research artifacts came together to create something in the industry that became highly successful. And you can see that on the one hand, you can do open source development, but also monetize it then as an end product. We will see how successful this company will be, of course, then, right? It's not clear what monetization will happen, but you can, like in Linux case, do both open source development and then also industry-based schemes together. Foundation models are also used a lot as components in other systems, so this is an important point here, that you can all of a sudden do model patching, model merging for different architectures. And this is what we are currently also curious to play around. All these experiments require supercomputing power, as stated before. So that's why the appeal of open source community here is also that it allows you to do common effort in producing those base models that avoids replication of the same expensive effort for each closed source place. So the scales that we were studying by the community in the case of OpenClip, for instance, are still rather modest compared to closed doors players. So here, the most interesting functionality arises pretty sure at much larger scales. We require then for this also larger machines to conduct experiments properly, and luckily we will get at least a newly supercomputing, a machine that is much larger. But so the community has to like intensify and also formalize these efforts, obtaining state-funded compute to keep pace with closed doors competitors. When we are talking about the issues in European Union to properly be on par with transatlantic partners in America, we lag far behind, but supercomputers in EU can become hubs to build such a community that is actually playing well along closed doors schemes like OpenAI, DeepMind, Google, and so on. And this leads also to open science form, which is then arguably a better take on it. We will see. To provide an outlook, so among Lion and friends, we are aiming then to go for a open source a backbone for foundation models that will digest all kind of multimodal data. So this is a common trend right now in the research field. We just would like to make sure that it will also happen on larger scale in the academia and do not then wander off again in the closed doors settings so that we cannot study it. We also have an AUTOML related project where we interacted with Frank Huta's lab already a bit, called Project Nucleus, that is about systematic search for strongly scalable architectures via AUTOML. And there we have just a problem that conveying such a search, if you make candidates large enough, is very compute intensive. So we have to solve there also compute resource problem to be able to conduct such research together. So our idea of the moonshot would be indeed building something like a successor of GPT-4 on European grounds in open source manner and give it to the community to study it, to play with it, and so on. That would disseminate the whole field, I think, very strongly, hopefully also leading to things like foundation models for semi-automated scientific discovery. So in chemistry and drug discovery, it already happens in some ways. And also give to the people this kind of personalized AI assistance to play around that also can go back to industry and lead to customized solutions that are monetizable, right? So I hope that this ecosystem of open foundation models will grow stronger, so and provide us a transparent and validated basis for research and industry as well. So safeguarded by this large community that are looking into these models, also in terms of reproducibility, but also in terms of safety. And this can become on European grounds, I think, really a good alternative to closed source schemes that could outcompete if we pull it in the right way, and also allow industry to close the loop to such strong companies like OpenAI and DeepMind that rather do closed source form. So I would like to acknowledge the whole Lion community, of course, but especially these people, my postdoc, Mehdi Cherti, and Professor Ludwig Schmidt, who drives OpenClip research community and also a strong Lion contributor. And I would like to conclude with a statement, so let's give it a try to build an open and safe AI foundations and you together using the power of open source and the power of widely distributed research community who we are. Thank you.
Okay, we've got time for a few questions. Frank has indicated he'd like to ask the first question, and he will also be demonstrating the proper use of the catch microphone, which has not pan-directional.
Yeah, so if you speak into this, there's this thing to speak in, then you hear it, this way you don't hear it, this way you hear it. So speak in there. And I'll demonstrate that by making a comment and a question. So the comment is, I'm super happy that Jenia is here as a representative of Lion and Lion.
We should put it in the wiki, Lion. So people do Lion, but Lion.
Yeah, so we haven't heard a lot about AutoML in this particular talk, but this day is for building bridges. And we really want to build bridges between AutoML and foundation models. As also talking a lot with sponsors, I heard, well, kind of all the money these days is going to LLMs, and AutoML is not really there. And that's one perspective, but it's not the perspective I would have. There is a lot of interactions between LLMs, foundation models, and AutoML, and we as a community should really just work hard to show that to the world. And there is this project Nucleus we have there, and there is a lot of other possibilities. So it's great to have Jenia here, and use the opportunity to talk to him, and let's really get on there with AutoML and foundation models.
Yeah, just one quick comment. I mean, of course, we were designing all the architectures so far by hand. So now convnets, transformers. I think the next breakthrough, like the breakthrough away from handcrafted features, would be then the breakthrough to well-designed automated architecture. So, and this we could try to do together.
Mm-hmm. Yeah, and another comment to industry folks who are hearing, well, AutoML is not really where the money should be, it's LLMs. If you want to serve LLMs, if you want to optimize them for all different kinds of use cases, fine-tune them for different use cases, of course it's AutoML, multi-objective optimization. So you have that argument already there directly if you get that comment and people want to rationalize AutoML away. But other questions?
It's a bit of a big one to catch.
Yeah, hey, Amazon folks.
So first of all, absolutely fantastic work. It's very inspirational to me. So when building an open research community, how do you drive community growth and ease of contribution while simultaneously maintaining project focus and quality?
Yeah, how do we do it? So we first make sure that the project we start are already rooted in different research labs as an ongoing activity. So we still haven't undertaken a track where we initiate something that hasn't been happening anywhere in the world. So it's usually some strong research lab that is already carrying it. And this is then the classical way to do it. So the lab has strong interest to maintain it. It's already the existing funding in there, or many labs actually together with a similar focus. And then you attract contributors that gravitate around this already existing track. And they get either indeed employed by the research labs, or get somewhere into an industry realm and attach to whatever the open source ongoing effort is with their own solutions that are maybe even closed source, but are still founded in into the base open source form that is developed, and so they actually rely on it being well maintained. So and then they put some effort in maintaining the open source code base back. So it's like for them cheaper. I guess this is the stabilizing factor here. So you have an open source project that all of a sudden becomes a backbone for different, because it's good. So this has to be the case, that it's actually good and reusable. And then people from different sides are ready to support it because they rely on it. Discord server, communication-wise, turned out to be a very easy way to actually keep people on track. So there are no organizational super wisdom. Just create those quick exchange channels and let people talk. Documentation and wikis are important. So it's really the same recipes like everywhere else. It's just that we have, I think, a good intuition for which projects and which people fit together. So this I cannot really teach immediately how that works.
Awesome.
Another plug for the conference Discord. There was another question back here. Maybe one more question, then we can move into the coffee break.
Where is it?
There was a whole group of questions over here.
I'm just gonna.
But now there's one over there. Nope. Maybe there's a more excited question over here.
Yeah. Hi. Yeah. So thanks for the great talk, and I agree. It's a really exciting thing that you built in there. And I was just wondering, so it's a follow-up question to Nick's question. How do you allocate resources to ideas? So who is deciding which idea gets compute resources and how much? Yeah.
So. I mean, this is solved by the existing peer reviews at supercomputing facilities. How we decide what is worth going, okay, we have, I don't know, dozens of senior research people who are hanging in these Discord channels and then exchanging, and then at some point there is an insight, okay, this is what we would like to invest most, this is second most, so we just talk. But then you have to write a grant for the facility, you explain yourself, you apply for a certain amount of compute time, and then people review it, and then you get cut some of it. So you have to live with what you get. So you have, of course, to have some peer review forms that are already set up in place. If it wouldn't be for them, then we would have to invent them again. So, right.
Okay, that's a good problem to have. Okay, so thank you, Jenia. And then